All right. I I've actually recorded this a few times already. Most of my first recordings, the audio didn't work. So even after I got one that I was happy with, uh, yeah, I got nothing. But now I'm using just my laptop microphone, which is going to sound horrible, and I'm sorry, but I want to record every day, and technical difficulties are part of the excitement of recording every day. Like that is how you get better, is by failing, and this fail. This is a fail. Um, but the whole point of recording, like the whole reason I want to get into this, is to record something for someone. Not just send vibes out to the internet. I want to have something for someone, and usually one person. I don't mean like something that would be useful to a group of people because I think it would be useful. I mean something that a person wants, needs, asks for, reference, that kind of thing. And you brought up earlier today that you wanted to see the parser I've been working on. So what better thing to start with than the parser I've been working on? Actually, there's probably plenty better. Doesn't matter. We're starting with the parser. Most parsers, when they're birthed in an academic's mind, are actually recognizers. Recognizers just say, hey, given a grammar and an input, could the input be produced by the grammar? Which is frankly stupid. It's the wrong question. It's not what anyone cares about, right? Like, that's not parsing, that's producing. We want to know, can the input be consumed by the grammar? But that's not how linguists look at this. And so parsers sort of always come at this backwards. The exception to this is PEG, story for another time. So when we get these parsers, or when we get these recognizers, we all we really wind up doing is sort of recording along the way what the parser thinks it could have produced, like the match from the input that is the justification. It's sort of like a proof of work, right? It just sort of remembers, just memoizes what it saw that made it think this was the production. We refer to that usually as an abstract syntax tree or a parse tree. And so right now, that's the state this parser is in. It's returning a parse tree. Now, you know me. You know I can't stand abstract syntax trees. Like, the whole reason you were parsing something wasn't to get a true or false, and it wasn't to get a proof of work. The whole reason you're parsing something is because you want to use it. And it would be very nice to have it parse into the thing you want to use. It just turns out that's not how people who write parsers think about the problem. And it frustrates me, and so that's why I always wind up writing my own parsers, which is where we are today. I set out to start to document this thing. You'll see I have the start of a comment up here. This comment's useless to anybody unless they already know what they're talking about specifically with this parser, and therefore that comment is only useful to me in as much as it's not useful to me either. So really the point is, I don't have any documentation yet. That will come. I don't have any pictures yet. That will come. And pictures and documentation would help explain this a lot. So instead of talking through the whole file, when I say whole file, this is the whole parser, and it is 350 lines, including that comment up front. 351. We'll talk about the rest of this, but right now I just want to show the algorithm for the parser. Now, obviously, when I show you the algorithm for the parser, you're going to be like, that can't possibly be it. I agree. That can't possibly be it. There's a lot built into sort of the dynamic piece of this, the states. But I want to talk through the parser because I feel like it just makes all the magic go away. And you're like, wait, is that really all it's saying? Yeah, that's all that's going on. So there's just not any magic left after this. There's just how the states work. And there are two kind of classes, not class, keyword class, but two kind of categories of states. We'll talk about both of those and how they work and why they're different in the coming days. But the end result of this is Once you understand how states work, and once you understand how states are produced and sort of get walked, this is very much a dynamic kind of once you understand that, there's just no magic left. It's just sort of like, here's how a state works. You understand if you want to create a new state, which, by the way, you almost never will. So the cool thing about this is people can absolutely extend this parser, no problem. Most people won't, but if you want to, it's trivial to extend this. All right, let's talk about this. So I do want to point out, so this is the parser. You see, this is the whole thing. This add thing, all that's doing is saying, hey, when you got a rule, here's how you insert it into the parser. All right, so each one of these lines would be a different add call if this was a valid parse, and I already had the parser. They can parse those files. It doesn't matter. Why is, that's not saved. There we go. I'm going to take an aside before we dive into the parse. So this add thing is not part of the parse. It's just part of the configuration. Yeah, it doesn't matter. This is the whole parse thing. We're going to come back here in just a second because I want to show that off. I hit Control Z here because I had done this as part of another thing. But just to show this, I didn't save this is my test file. It's written in Jasmine, but behind the scenes it's Wallaby. Wallaby is brilliant, and everyone should have it. I love Wallaby. I will never live without Wallaby. I'm not sponsored by Wallaby. I wish to God I was sponsored by Wallaby. It is a fantastic, fantastic product everyone should be using. Because I didn't even save this file. It was already running the test. I hit Control Z and put it back. That disappears. You get these little debug things right in play. Oh gosh, the debug can go backwards in time. Thank you, God. How has this taken so... Anyway, it doesn't matter. Wallaby is beautiful. We'll talk about it some other time, not sponsored. Here we go. Parse. This is it. And you'll notice this while loop, which is really the sort of crux of the whole thing, it does some stuff where it does predict, complete, and scan. Down here we got predict and complete. I was stubborn and refused to put a null terminal character here on the input. I refused to have this artificial end to my input, which would let me merge these two loops and turn this into like a 10-statement parse. I was stubborn. I hate modifying the input. I'm going to add it eventually because while I hate modifying the input, having a whole parser written in 10 lines is just pretty damn sexy. But the point is, I didn't do it. I want to do it like right this second, but it's not. I'm not going to. I'm not going to do it. I'm not going to do it. The point is, this is the whole thing. So really, we just have to talk through this thing. Early is built on this concept of states. Now, my states, strictly speaking, aren't the same as early states. We'll talk about that more later. But the concept ports pretty well from early. So the idea behind a state is it's just where are we in parsing a particular rule or matching a particular rule. So if we were right here, so we were just after the ident and matching this line. So imagine we were reading this line and we were right before the equals. So this is the character we're on while we're parsing. And this is the rule we think we're matching. The state would be, hey, we're right here. Okay, so the state sort of remembers both where you are in the expression in the right-hand side, and it remembers where you are in the input as well. Okay, so you get sort of this state is a collection of things that basically says, here's exactly where we are in the parse, but at any one time, early is sort of special and it's trying to parse every possible match it could. So at any particular time, it could think we're in 17 different places, or 115 different places, or 1,000,000 different places in the rule production for this input given this grammar. Well, whatever the set of states is, we initialize it with this thing called a root state. But whatever the set of states are, we're just going to iterate over them until we've processed all the states for this character. So we're going to loop over the characters. We're going to take this thing called a reference cache. This reference cache is an optimization, and we can talk about it more later. but it's just an optimization. So it's not critical really. We are making a new one each character, which sounds expensive, but it's a hash map, and it's a hash map that's going to be at most, the size of your grammar. And when I say the size of your grammar, I mean the number of rules. So the biggest this hash map could ever be is 10 elements. Sorry, I keep clicking on test. So it could be 10 elements. So in general, this is an optimization that way out. I could probably find some way of clearing the hash map or something. Like, I could find ways to make this operate a little bit faster without destroying it every time. But destroying it every time works right now. And in all fairness, this whole algorithm is super cheap. And creating it just hasn't been the thing to try to optimize away. So, point is, we build a reference cache. We'll talk about that more later, like another day. Story for another time. And what we're trying to do when we're processing all these states is figure out which states actually go to the next character, which states consume this character successfully. And so when we look at a state, there's sort of three. State is, again, a bad word. It's sort of the set of operations that could happen. A particular state could only do one of these three things successfully, at most. Right? A state could only predict or complete or scan. What predict means is say, hey, the next symbol in my list. So if we were parsing rule, or we had just consumed ident, the predict would say, hey, I think we've got an equals coming. It's predicting that the next character will be an equals. Right? So that's what predict is. Just what do I think is coming next? What states should I be expecting next? So I'm expecting equals next, right? So it's not consuming it. It's not saying I see an equals. That's what scan does. Scan says, hey, this character, the previous guy said I should predict something and I saw it. Put me in the next round. That's why we're putting in the next instead of state. But if we predict something, it's staying in the same state. We haven't consumed the character yet. We're just saying, hey, I think the next thing is going to be an equals. Or, hey, I think the next thing is going to be an identifier. If we actually finish a rule, well, that completed it. So if we make it to the end here, that completed it. And we just tell the person who created us, the state that predicted us, when we complete, we tell them, hey, advance your pointer. Okay? That's all that's happening. Complete is super simple. You literally just tell the parent, hey, advance your pointer. Predict is super simple. You literally just say, hey, here's all the possible next symbols I could have. Usually, it's one. At most. Right? And then scan says, hey, this character that's next in the input, I was looking for that character. Add my next state into, well, it's not even my next state. Add me to the successful candidates for the next one. So the only people that show up here, the only people that get moved into the state for the next things are the ones that successfully consume the character. Those are it. Not any predictions, not any completions. The only you have to consume a character, or you don't get to graduate to the next level, the next character. Which means in practice, very few things move to the next character. If you don't move, if you don't have something to predict, if you don't have something to complete, if you don't have something to scan, you're just lost. You're just disposed. You're just garbage collected. Right? This thing has no real memory to it. The only memory is built into the structures themselves. Every state remembers the parent that called it so that when they complete, they can trigger their parent to advance. But their parent doesn't remember the children. So when they say, hey, I'm completed, hey, parent, advance me to the next thing, parent says, gotcha, and they disappear. The state is no more. When these states actually produce stuff, everything that happens in predict, complete, scan, these don't preserve the state that was just used. If that information isn't carried forward into another object, it's gone. It's just garbage collected. And most of the storage on these guys is actually built into the actual rules, right? So the rules store all of the information that's true about rules, and they don't change the whole time. The only thing that changes over time is these states, and that's really just a position, a pointer. That's it. So you just get creating all these objects that are effectively pointers, and they just get disposed whenever nobody references them anymore, which is kind of all the time. Either they didn't match a next character, and so they're lost to eternity, or they completed and they're lost to eternity. And that's the whole parser. That's it. It's just going to keep doing predictions, completions, and scans until it finishes the input, and then it's going to say, hey, we might have some predictions or completions that kind of need to clean up. Let me find a root state and return you the result. Right? Because a root state, eventually whoever he called, whoever he started, whoever he predicted, that prediction will complete and roll back up to him if it was a successful parse, and he will complete and therefore trigger. He'll move his state because he'll advance into the current state set, and that's it. That's the whole thing. Everything else to here are these little 2 or 3 line methods on what it means to predict for this particular state type, and what it means to complete for this particular state type. Like, it is just sort of ridiculous how trivial it is to create this parser. And I'm quite confident. I still have a couple optimizations I'm really confident will work, and that I want to try with and experiment with, that will turn this into just nonsense fast. Earley was built to be object oriented. It's kind of blowing my mind. So that is this particular thing. Again, can't stress. I don't know if you noticed, but all of those little bullets on the side, that's all Wallaby telling me, without even running anything, just because it's on, that is Wallaby telling me I am 99.17% covered. Oh, Wallaby. So, I hope you enjoyed it. I know this was long. I know I said I was going to stick to 10 minutes. A lot of the previous recordings I did were like a half an hour, so yeah. I don't even know what feedback I'm looking for this, really. Please do feel free to share if you have any feedback, because I, of course, would appreciate that. But really, this is just because you asked me about it and I wanted to share. So, yeah, hope you enjoy, man. And talk to you later.